Hello all. Today I'll talk about endogeny for the K-mean recursive distributional equation. This is joint work with Vijay Subramanian and Rajesh Sundaresan. The broad motivation is to understand when belief propagation, a local passing algorithm, converges for a certain class of random optimization problem. In particular, we are interested in the minimum weight K factor problem. So consider a complete graph with n vertices and in IID edge weights. In particular, we consider the edge weights to be exponentially distributed. A K factor is a spanning subgraph where every vertex has degree exactly K. The goal is to find the K factor with minimum total edge weight. For K equal to 1, this corresponds to the minimum weight perfect matching. And for K equal to 2, this corresponds to the minimum weight cycle cover or the two-factor graph. So this is a natural family of random optimization problems, and we want to understand whether a local algorithm converges to the optimal value. The local algorithm of interest is the belief propagation algorithm, abbreviated as BP. BP sends messages along the directed edges. For the factor problem, the message update is essentially look at all the neighbors except the one you are sending the message to, subtract their incoming messages from the edge weights, and take the kth smallest adjusted cost. After several iterations, each vertex chooses the kth neighbors with the smallest adjusted cost. The appeal of BP is that it is local and parallelizable. However, we need to theoretically guarantee that BP indeed does converge to the optimal value. So here is a roadmap for the proof of convergence of belief propagation. And this roadmap is from the work of Sales and Shah, who proved the convergence of BP for K equal to 1, which is the minimum weight perfect matching. The convergence proof is organized through the limiting infinite tree or the Poisson weighted infinite tree, which we'll call as PWIT. Essentially, one considers the limit of the belief propagation algorithm as the number of vertices goes to infinity. Uh, so as the number of vertices goes to infinity, one can show that a complete graph with exponentially IID edge weights converges to an infinite tree called PWIT, which will be described later. And we study this belief propagation algorithm on the PWIT. Uh, and then once the problem is transferred to the PWIT, we study the belief propagation algorithm on the PWIT. So, which is highlighted by the arrow number 3. The proof of the convergence on PWIT uses a mathematical property called endogeny, which will be the key of our key focus of our work. Finally, using the fact that the optimal value on the finite graph converges to the optimal value for the PWIT, Sales and Shah show that as t goes to infinity, the belief propagation algorithm on the finite graph converges to its optimal value. Uh, Now let's uh, look at the PWIT formulation. Before going there, I'll describe a recursive distributional equation. A recursive distributional equation is an equation where the left-hand side and right-hand side of the equations are probability distribution. In particular, we are interested in the following equation. Let psi j be the unit points of a unit rate Poisson process. Then consider this equation where x is distributed as the kth minimum of these adjusted costs psi j minus xj, and xj IID copies of the random variable x and is independent of the driving noise psi j. Now we'll introduce the notion of PWIT and we'll embed this recursive distributional equation on the PWIT. On the PWIT, each vertex has infinitely many children with edge weights given by independent Poisson processes. At each vertex, we can define a random variable xv, which is the kth minimum of the adjusted cost psi vi minus xvi, where I corresponds to the ith children of the vertex v. This is a recursive tree process, which is in fact a generalization of a Markov chain. Endogeny. Now, the property we are interested in is called endogeny. And endogeny means that the root value x phi, or the value of any vertex v, is determined by the edge weights of the tree alone and not by the values of its children. In other words, once the PWIT edge weights are fixed, there is no extra randomness coming from the boundary condition at infinity. This is the key property needed to prove convergence of belief propagation on PWIT. Now, instead of proving um, instead of proving endogeny directly, we use the Aldous-Bandappadhyay condition known as bivariate uniqueness. Uh, so consider the bivariate version of the recursive distribution. We take two copies x and y driven of the k-min RDE. So you can see that each coordinate is the kth minimum of the adjusted cost psi j minus xj and psi j minus yj. But the important point to note is that the driving noise psi j is common for both the distributional equation. Uh, so a diagonal solution for this bivariate fixed point equation x comma y is a solution where x comma y is equal to x comma x. In other words, x is equal to y almost surely. Uh, Aldous and Bandyopadhyay introduced a criterion where they showed that the structural property endogeny, where the root value is independent of the boundary conditions or at the infinity, is equivalent to the bivariate uniqueness. The nice thing about bivariate uniqueness is that it's more concrete and easier to test. So we use this theorem and we prove the bivariate uniqueness for our K-min RD, which is the main result of our work. So K, a little bit of history, K equal to 1, which corresponds to the minimum weight perfect matching. The endogeny property has already been proved by Antar earlier. However, for K greater than true, the same approach does not generalize due to the non-linear structure of the fixed point equation. Our contribution is the following. We provide a proof of endogeny that works uniformly for all K greater than equal to 1. So here is a brief proof sketch. Consider the CCDF, cumulative of CCDF of the univariate fixed point x and the joint CCDF of the bivariate fixed point x and y. We'll denote them by s and x respectively. And we define the bivariate error delta x is as the logarithm of s over g. The first reduction, which is essentially the same argument as k equal to 1, is that bivariate uniqueness hold if and only if g is equal to x for all x, almost surely. Uh, if and only if the bivariate error is identically equal to 0. So the problem of proving endogeny is reduced to showing that the error fixed point has only the 0 solution. Uh, the rest of the proof goes into manipulating the fixed point equation. So the first step is to derive the fixed point equation. Without going into the details of what the fixed point equation is, the main thing to note is that the fixed point equation has a nice probabilistic interpretation. And what we do is we borrow an idea from Parisi and Weisland from the univariate uniqueness, and we convert this system of this fixed point equation into a ordinary differential equation. Finally, we construct a univariant of the first two variables of the system, univariate invariant for the first two variables of the system, and reduce the dimension of this fixed point equation from 4-dimensional system to a 2-dimensional system involving r plus tilde and r minus tilde. Uh, so the main observation we make is that any solution to the fixed point equation is a solution to the ODE. However, not all solutions to this ODE is a solution to the fixed point equation. In particular, for ODE solution to be the solution of the fixed point equation, it must satisfy this admissibility condition. And the rest of the proof goes into showing that only delta equal to 0 satisfies the admissibility condition. And the proof strategy involves constructing a monotone quantity uh, to rule out admissibility. Thank you.